Okay, good day to everybody, and thanks for your introduction. Too kind for me. Anyway, I am very happy to have the possibility of this short chat on two-particle transfer as a possible signal for shape phase transition. It is well known that two-particle transfer reactions are the standard obvious tool traditionally to study in a dynamical way the pairing degrees of freedom of nuclei, and in particular for the study of the collectivity that the pairing interaction is inducing on the ground state of a system, and in particular on this. Therefore, on the enhancement of the transfer probabilities with respect to unperturbed non-collective state. From a connection between reaction and theory, the basic idea is that the two-particle transfer probabilities are somehow proportional, or at least dependent on the pair strength, and the pair strength is nothing but the square of the matrix element of the pairing operator between our A system and the A+2 or A-2 system. In general, the pairing properties of a nuclear system are characterized by what I call the pairing response of the system. That is the matrix element of the pairing operator between my initial ground state and all the 0+ state of the A+2 or A-2 system. Typically, the pairing response is illustrated in this figure, where I just take the matrix element of the pairing operator between lead-208, and in this case lead-210, taking all the 0+ state in lead-210, taking the matrix element square, and comparing the unperturbed results obtained without the pairing with what theory predicts if I switch on the pairing degrees of freedom. These calculations were done in RPA or Tandanko, doesn't matter. I presume that any theory will give more or less the same result. The important thing is that you see that the switching on of the pairing interaction is moving a large fraction of the strength to the ground state, with a large enhancement of the pairing strength to the ground state with respect to all the other state. And the result of this typical result is that you see that in a TP reaction, for example, in T118 going to T120, and you can see that the transfer to the ground state is by far order of magnitude larger than the transition to all the other state. And you can see in this case, that the first excited state is very, very weakly excited with respect to the ground state. So in this case, which is a case in which the system is superfluid from the point of view of the pairing, practically all the strength goes into the ground state. But I just mentioned that there are other cases in which there are population of strong other 0+ state. This is close to around closed shell for excitation of two particles to all state, and there are cases in which other excited 0+ state are competing with the ground state. The basic problem that, in my opinion, is not completely solved is how to extract from the measure cross-section information on the pairing enhancement. This is due to the fact that at variance with other kind of reaction like Coulomb excitation, the the reaction mechanism is very complicated, and the possibility of extracting spectroscopic information is not obvious. And this is partially due to the fact that the problem is essentially at least a four-body problem. There are two cores and two particles, and most of the theories and models are trying to reduce these complex four-body problems at least to a more trackable framework. Okay, and as I said, there are many approaches, and I would say that still there is not a convergence, universal convergence on which model one should use. I just remind that the most popular are the one in which it is the successive single particle transfer that dominates, and this approach is based on the dominance of the mean field. A different approach is what I can call cluster transfer. The two neutrons or two protons are transferred as a unique object, and this approach is based with the idea that it's the pair interaction that dominates. Okay, in the case of the sequential two-step, in which the external mean field is transferring one particle after the other, the pair interaction is inducing anyway a coherence interference of the different paths through the different intermediate state due to the correlation in initial and final function. And as I said, the basic idea is that it's the mean field that provide the main and dominant framework for this kind of reaction. And this typical approach, I don't want to enter into detail, but if you make expansion to second order in the transfer potential, you get this famous simultaneous sequential and orthogonality term, and it has been shown that in most of the cases, the simultaneous and the non-orthogonality tend to approximate, cancel each other, and it is the sequential that dominates. These are calculations done by the Milano-Sevilla group, which made a lot of works on this, and you can see from the figure that essentially the total final calculation that include all the terms practically coincide with the result of the successive. This is one line of approach. A different line of approach is the one based on cluster transfer, and this is strongly suggested by the fact that the pair interaction is inducing a radial correlation of the pairs. The two particles, due to the pairing, tend to be close together, also in the initial and final system. And this approach will be obviously dominant in the case in which the pair interaction will be extremely large or even going to infinity. And in this case, what you do is just to take the overlap of initial and final wave function with the 0s internal wave function for the relative motion. Also, in this case, the pairing is inducing correlations and inducing enhancement, but the kind of enhancement that you get in this approach is different from the kind of enhancement that you can get in the other approach. So the total final result, in my idea, is that the subject is not yet completely clarified, and sometimes it's just a question of taste to use one model or another. What I certainly am ready to say that one model excludes the other one, and it's very dangerous, in my opinion, to sum the contribution of one approach with the contribution of the other one. Anyway, still a lot of work have to do before we move to the phase transition. I just mentioned three line of research that I find fundamentally for two particle transfer. One is the way in which the continuum enter in this game. if in particular, if I go close to the drip line, typically reaction could be helium-6, PT, helium-4. In this case, as I said, I go via the intermediate state, but the intermediate state, which is helium-5, is unbound. And so the problem is how should I treat the continuum? Will the fact that it is a continuum and not a normal set of bound state will change the picture? And that is, to me, something to be clarified. The second thing is the search for highline pairing vibration. As you saw before, I don't know if you noticed, in the pairing response, due to the shell gap, not only the ground state get a strong collectivity, but there is also the possibility to have a collective highline state, which is parallel to what you get in the particle hole channel with the normal giant resonance. And this is the giant pairing vibration, which is a state which has been for long search, and there is a lot of work done, in particular in Catania by the Newman group. And I just show a picture with, you can see in the middle of a bump of many other states with other multipolarity, a little bump that according to the angular distribution could be a giant pairing vibration. So it's a rather delicate and difficult measurement, but very interesting. And the third line of research that I just quote is the interplay of T=0 and T=1 pair transfer. I'm now thinking always of the T=1 pairing, but of course you can also have transferring of neutron, a proton and a neutron, and also the enhancement in this case, the interplay between the T=0 and T=1 transfer is it's certainly interesting pictures. But let's now move to my main problem today, which is the problem of the phase transition. Phase transition in which degrees of freedom? Well, the nuclear system is at least characterized by two phases. One in the phase, in the shape, degrees of freedom. We always talk about spherical nuclei, deformed nuclei, whatever. The other is the pairing phase from the point of view of the pairing degrees of freedom. Systems are normally called normal or superfluid, okay? And by changing, for example, the mass along an isotope chain, or by changing the angular momentum of the system, or by changing the temperature of the system, you may have a transition from one phase to another phase. So from normal to superfluid, or from spherical to deformed. And in addition to the normal signature, which it can be, I don't know, I just mentioned here the ratio E4, E2, or the B2s. Also, the two-particle transfer may provide a hint and a possible signature for this transition. This is the usual picture that show or try to show the correspondence and the similarity to what is happening in the shape degrees of freedom with the angular momentum, and what is happening in parallel in the pairing degrees of freedom in the gauge space. But so in both cases, you can have spherical and deformed in the normal space. You can have sphericity and deformation in the pairing degrees of freedom. Okay, so in the pairing degrees of freedom, by looking at the ground-to-ground matrix element, so this is from the ground state to A+2, you can have a round closed shell. Normally nuclei are having a normal phase from the pairing degrees of freedom. Now, when you are in the middle of the shell, you can somehow go into a new phase, which is the superfluid phase. And in that case, you get a strong enhancement of the pairing matrix element. Okay, such a picture, in reality, if you make, you can yourself try to make a calculation. This was our calculation by the group in Jose, calculation with SCRM for thin isotope with a certain density-dependent pairing interaction, and by you plot this pairing strength, so always the matrix element of the pairing operator between A and A+2, and in fact you can see that the result seems to show what I've seen, what I was talking just before, a behavior like vibrational in around closed shell, T100 and T122, and a sort of pairing rotational smooth behavior in the center of the cell. So from the point of view of the pairing degrees of freedom, it's clear that transfer processes are a good tool for studying phase transition in the pairing degrees of freedom. But what I would like to see is whether the two-particle transfer processes can be also a signature for shape phase transition. Okay, and to do this, I have chosen the interacting boson model as a framework to describe the nuclear structure properties of this system. As you know, the IBM is based on the idea of having a number of S and D boson with L=0 and L=2 pairs that are interacting via a two-body boson Hamiltonian. And this picture is a famous triangle of the IBM, which tried to show that with specific choices of the parameters of the Hamiltonian, you can get Hamiltonians that satisfy specific dynamical symmetries. And in that case, you can solve analytically your problem. And in particular, there are three possible cases like that, and which are the one corresponding to U5, O6, and SU3, that give rise to three specific shape. In one case, we are spherical. In the other case, we are a axial symmetric rotor. In the other case, you are in the gamma soft Willett and Jean model. Okay, and any system is probably not satisfying perfectly one of the dynamical symmetries, but you can think of possibility of moving, for example, varying the mass along a definite isotope chain from one symmetry to the other and having a sort of transition, shape transition. Now, if I want to calculate two-particle transfer matrix element within the IBM, of course, I cannot use the standard Eidaga operator, which is a fermion. I have to map this fermion operator into a boson operator. And the simplest idea is just to take the lowest term, which is the S-DAG operator, which is the operator that creates just a pair of L=0. So how can I describe in a very simple model a phase transition? Okay, I just take a the most simplest model that I can do. I made the suggestion that if I have 1, 2, or 3 pairs, okay, my system is spherical, and I take that going from 4, 5, 6, then the system become deformed. So I describe up to n equal 3 the system as within the U5 Hamiltonian, and in SU3 after. And then I calculate the matrix element of the S operator between n and n plus 1 pair. Okay, now what's happening? It's happened that in the spherical region, okay, the matrix, the pairing strength increases linearly as expected from the U5. And similarly, if I go into the deformed region, the pairing strength increases linearly. But something happened precisely when I have in the jump from the spherical to the deformed region, because I'm going from a ground state which is spherical to the next ground state which is deformed, and this gives rise to a decrease of the probability of the transfer strength, and the calculation shows this peculiar decreasing of the ground state transition. And in parallel with this, while in the spherical or in the deformed region, most of the strength goes into the ground-to-ground transition. Precisely at the transition, there is a strong population of an excited state. In this case, the beta, which I call the beta vibration. So the pairing strength seems to be a clear signal of this phase transition, in this case from sphericity to axial symmetry. If I want to make it in more detail, I could take a variational Hamiltonian, which is a combination of the Hamiltonian for U5 and the Hamiltonian of SU3 with some parameter. So you understand that when alpha is 0, you are spherical. If alpha is 1, you become deformed, and then you move the alpha going from 0 to 1, and then if I look at the energy surfaces that correspond to this different situation, you can see that you go from some energy surface as a function of beta, the usual deformation parameter, which has a minimum in 0, so it's spherical, and a certain moment, at a certain critical point, there is a first order transition, and my energy surface having a minimum for the formation. So at a certain moment, the system make this phase transition from sphericity to deformation. So if I now associate this alpha change to some variation with the mass along an isotope chain, okay? For example, if I chose in such a way that the critical point in this case is between 8 and 9 pairs, okay? I can see that I go, if I look at the lower figure, I'm from U5 to SU5. As long as I'm spherical, all the strength goes into the ground state. If I am strongly deformed, most of the strength goes to the ground state and only a little bit into the beta vibration, the beta vibration. But precisely at the critical point, there is a fragmentation of the strength. Only a little bit of the strength goes into the ground state. Most of the strength goes into excited state, and also not just to a single state, but to a number of states. Okay, so this is obviously a very naive, simple picture. Let me, well, this is just the same where you see better the behavior. This is the pair transfer intensity. Ground to ground is the largest, much larger than the excited state, and the same when you are in the deformed region, but precisely at the critical point, you have a strong decrease of the ground to ground and a strong increase of the ground to excite state, and also, as I said, a fragmentation of the strength. Okay, let's make the situation at least a little more complicated. Instead of having just these very simple models, let's take a case, a real case. Let me take the samarium isotope, and these are results for the energies of the different spectra of the different samarium obtained by fitting a general IBM Hamiltonian for each isotope. So let's say that these theoretical calculations are very close to the experimental data, and then you see that in fact in samarium, in the low mass samarium, there is a spectrum that resembles a vibrator. You see the 2+ and the triplet 0 to 4 excited, and then if you go to higher mass, as you know, you start getting a deformed, a nice rotational band, and you see the effect, the behavior of the first excited 0+ that has precisely the minimum in correspondence on the phase transition. And if I calculate the pairing strength, I precisely in this case see the effect we were talking about, a strong decrease of the ground to ground, okay, and the appearance of a strong excited 0+ in this case in samarium 150. What I can see from this figure is that I don't see any fragmentation in this more concrete case, and most of the excited strands stay in just one state. And if I compare this signal with other signals that also characterize the phase transition, for example, the B2 between the second 0+ and the first 2+, which is strong if you are in a vibrational picture, 2 phonon going to the 1 phonon, and then dropping to 0 when the system becoming deformed. So, or the energy, as I said, of the 2+, is also an indication that here around 150 you get a change of phase. But as you can see, the signal given by the pair strength is as strong as other signature. Okay. If these are pairing strengths, so matrix element of the pairing operator, what happens if I now calculate really cross section? Okay, and these are calculations where one has moved from the pair strength to cross section within a fully microscopic approach with simultaneous successive contribution with the 2-neutron amplitude provided by the IBM, and here you finally compare. Sorry, something happened. You finally compare experiment with data. The red dot is the cross section for 0+ state, and the black one is the calculation, and you don't get exactly the experiment, but the qualitative effect is certainly reproduced. There is a kink, negative kink for the ground to ground, and the positive maximum for the excitation of the first 0+. Okay, so I would say that in this case, the cross-section confirm what is predicted by the nuclear structure, stuff. Of course, all these calculations are difficult because you can change optical parameter. You go into another angle, scattering angle, and you change the bombarding energies. So to get perfect results is extremely difficult. But I think that from a qualitative point of view, I would honestly say that the signal that something happened at 850 for samarium, between samarium 148 and samarium 150, that something happened. It's clear. This is not the only scenario that I can choose. In the scenario that I've described so far, I have a unique system that changes its shape. So it was altogether spherical and becoming altogether deformed. Okay, but I have another possibility, another scenario, the one of shape coexistence, with the idea that I can suppose that in the same system there are the presence of states with different shapes of the formation. For example, in the same system, in a narrow excitation energy range, I have a spherical system, but also a deformed. The existence of this different configuration is normally associated with the particle hole excitation across the shell closure. And typically, I would say, naively, vibrational-like states correspond to zero particle, zero hole excitation, while the deformed one are associated with at least two particle to hole excitation. Okay, and when both families of state cross in the ground state, then the ground state experience an abrupt change of the formation with the consequences in two-neutron separation energy, in quadrupole moment, and so on. But as I will show, also it will make a difference in the two-particle transfer cross-section. Okay. Again, let me make a very simple case. Let's suppose, starting with a simple two-level model, as I suppose I make the hypothesis that my ground state is a combination of a system with normal particles, okay, plus a second state which is due to two particle to hole. In a boson picture, my two particle to holes is increasing the number of pairs. Here you can see the figure. I have 3 pairs for normal system and 5 pairs with for the deformed system. And then in addition to this state, I have the orthogonal one, which will give rise to an excited state. So what's happening if I take a mixing between the two, and I suppose that along an isotope chain, the mixing term changing from 1 to 0, which means that there is a crossing of the normal state and the deformed state, okay? And the effect of this is that if I now calculate the matrix element of the pair operator, again, I can see that although I was expecting a linear behavior for the ground-to-ground, in the point in which there is a crossing of the two kind of states, I have a cross-section that goes definitely down. And on the other side, there is a strong population of the orthogonal excited state. So again, there is a signal at the crossing point. As you can see, the signal seems to be very similar to the signal that we were having in the normal case of phase transition. So of shape phase transition. So this simple model seems to show that the shape coexistence in the case of crossing of the two configuration give rise to something that apparently looks like a shape phase transition. Let's go into more complicated case. Okay, how can I treat? Again, I will use the IBM with extension to configuration mixing, and the standard IBM is then modified to deal also with particle Hall excitation, in particular to particle to Hall excitation. In this case, the original Hilbert space based on n valence bosons is enlarged to a sum of the original n state with the n+2 state of the other kind. So the n+2 space, as I just mentioned before, correspond to considering the two extra bosons coming from the promotion of a pair of protons, for example, across the corresponding shell closure, generating an extra boson. Result is that my Hamiltonian will be a sum of an Hamiltonian that describe the normal sector, and Hamiltonian that describe the intruder sector, and then there will be a mixing between the two sectors, in that making such a way that the normal states will in general mix with the other one, and the parameters of the normal Hamiltonian, the parameter of the intruder Hamiltonian, and the parameter of the mixing have to be fixed for each nucleus. Let's see a case, just a case. The typical case is zirconium isotope. Here you can see the prediction of the different state with different multipolarity as a function of the mass. Okay, you can see that a 0+ state come down, and of course you might think that the state mix, or eventually they cross. And if you see the calculation for, you can see from this figure that shows the regular content, you can, of the ground state, you see that up to a certain moment, my ground state has a 100% regular content, which means that it remains spherical. And after a certain moment, it has 0 regular content. So it has 100% of the intruder configuration. So it means that the ground state has become completely deformed, and vice versa. The excited 0+ here, up to a certain moment, correspond to a intruder state, and at a certain moment, this other 0+ is becoming the original regular content. And in fact, if I look at the prediction for the energy of the two states, you can see that the normal state, which is the black line, at a certain moment crosses with the other one, and the intruder state becoming the ground state. Well, how does this affect the pair strength? If I now calculate the pair strength, so the matrix element square between A and A+1, and I can see again the usual picture. The fact that the situation favor the ground-to-ground transition, but precisely not at the crossing point. At the crossing point, the ground-to-ground goes becoming relatively small, and there is a prediction for a strong population of the 0+ state. So in this figure up, you can just show, if I call the blue one is the spherical, the red one are the intruder. Between 98 and 100, there is an exchange of the spherical with the deform, and the consequence is that from 98, I will have a strong population of the excited state and a small population of the other state. You may say these are just simple calculation with are not simple, but you may not like the IBM kind of approach. You can move, for example, to other calculation. What is reported here are the calculation of the Tokyo group with the quantum Monte Carlo large-scale shell model calculation, and their calculation also show that between zirconium 98 and zirconium 100, there is an exchange of the formation. The ground state in zirconium 98 is spherical. You can see from this energy plot in the beta-gamma plane, and the excited state is deformed, but this deformed state becoming the ground state in zirconium 100. Now, if you do a calculation by using 1 and 2 particle transfer amplitude provided by this Monte Carlo calculation, then you can see that in fact you get strong cross-section for example, TP calculation up to 98, and when you at a certain moment you get the crossing, then you go your ground-to-ground cross-section becoming practically zero. So also more sophisticated calculation show precisely the same signature at the point in which there is this crossing term. Okay. Of course, you don't need to have always crossing. You can have shape coexistence with no crossing and also no mixing. This is the case of mercury isotope. If you look at the figure and just the energies of the second 2+ and this parabola that get a minimum, then you can think that you follow again the same behavior that we saw in zirconium, but in this case the calculation which I've done in this case with the IBM with the intruder configuration show no crossing between the normal and the intruder state, and also the regular content of the ground state, as you see, is practically always 100%. So there is, first of all, no crossing. There is no small mixing in the two configurations, and the result is that there is practically no effect in the pair strength behavior. So the ground to ground remain always the dominant transition, and so this shows that pair transfer is a good signature, but it has always to be also confronted with the other experimental data or other quantities, because it's an important signature, but cannot be the only signature, existing signature. Let's see another case, and this will be honestly the last one is platinum. Also, platinum is a case in which you have shape coexistence. In this case, there is certainly mixing between the normal configuration and the intruder configuration. Okay, this can again our calculation with the IBM with the intruder configuration. If you look at the regular content of ground and excited 0+ state, you can see that in a large fraction of the mass, there is practically a 50-50 or large mixing between the two configurations. There is also crossing between ground state and excited state, but the fact that both states are strongly mixed, making such a way that at the end, if I look at the pair strength, I get only small signal in correspondence of the two crossing point, but not such a strong effect as we have seen in the other case. So if I conclude the thing, is that I hope that I gave you at least a suggestion that the pairing response, which is tested into particle transfer reaction, can give a strong constraint on the nuclear wave function, and the effect is amplified in correspondence of critical situation. And critical situation, I have shown two critical situations. One is in the normal shape phase transition, and the other one is when there is a crossing with into the state with abnormal population, in both cases of excited 0+, and the weakening of the ground state transition. Okay. In spite of this clear signature that something has happened there, okay, so far it seems to me difficult to clearly disentangle the shape coexistence picture from the normal quantum phase transition only using the 2-neutron transfer intensity. So 2-neutron transfer intensity are very important, can give a good signal, but cannot completely be the only signal, in particular for distinguishing these two possible scenarios, which are shape phase transition or crossing of coexistence of two different shapes. Okay, from my point of view, that's all, and I thank you for the attention. And these are a number of people that have been involved in this meeting. Okay, thank you very much.